said, hey, you, let's do some diffie-Q. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some diffie-Q. In this video, we'll look at Taylor series. This is something you would have covered in a previous class, most likely Calculus 2. And now in differential equations, we're going to use series to solve some diffie-Qs. So let's review. Simply put, the Taylor series of a function about a point looks like this. Now, of course, since we're going to be finding derivatives, we need to have a function that's infinitely differentiable. It doesn't matter if those derivatives eventually become zero, we just need to be able to continually compute derivatives. The other thing to note is that we will be looking at this Taylor series about a certain value, a in magenta here. So when we write out the series, we have the derivatives in increasing order, evaluated at the point a. Then we have x minus a to increasing degree, and then we'll be dividing by an increasing factorial value. Polynomials are very nice functions. They're continuous everywhere, and you can really understand their shape well by looking at roots and so on. The next step up from that is functions that look like their Taylor expansion around given points, because the Taylor expansion really is just a polynomial. Once you take the derivative and substitute in a given value, divide it by a factorial, this is all just a number. Just like this is a number, just like this is just some number. Then we're taking x minus a squared, and so on, but those are just polynomials, so you have linear combinations of polynomials. So Taylor expansion is just a polynomial. So you're saying take a function and generate this polynomial version of that function. And sometimes the polynomial you generate, this Taylor expansion, will accurately simulate the function itself. The functions that are locally like their Taylor expansion are what we call analytic functions. That is, around a given point, if we take the Taylor expansion of a function around a, when you stay around a, that function and this polynomial are essentially the same. So if you look locally at a function, it looks basically just like a polynomial. Now let's do a computation right away. Suppose we want to find the Taylor series for this function about this value. And again, we always have to look around a certain value, because Taylor series are in some sense a local approximation of a function. First, we just fit the formula, saying that we're going to need the zeroth derivative, which is just the function itself, the first derivative, the second derivative, and so on. We go ahead and we compute the zeroth derivative, which is just the function itself, then the first derivative and the second derivative. And then we have a general formula for the nth derivative. It looks like this. And whenever you can find a general formula, you want to write it like that, because then you don't have to keep finding derivatives. You can just use the single formula. If we substitute in the value of 3, of course, we get this, and a little simplification gives us this. So what we've said so far is that around 3, this function has the Taylor expansion as a general formula like so, and then we found in particular the nth derivative evaluated at 3 looks like this. Therefore, if we go ahead and we use that formula, we can say the Taylor expansion is this in its compact form, and if we start writing out the terms, it looks like this. Now let's look at some common Taylor series. Each of these are the Taylor series of a function centered around x is equal to 0, or having an a value equal to 0. The three most classic ones are the exponential e of x, which has this Taylor series expansion about x is equal to 0. Cosine looks like so, and then sine looks like so. And I spaced it out in such a way that you can see that there's a correlation between sine, cosine, and exponential. It's from here that one can generate what's called Euler's formula. This is exactly as if we took I theta, substituted it for x, did the computation, where now x is I theta, and if you square I, of course, you'll get -1. If you take I to the fourth, you'll get 1. I cubed is negative I, and so on. Then you can show that there's a way to match cosine and sine up with this Taylor series. So writing each one of these components in its Taylor series will reach an equality. Another one worth noting is this 1 over 1 minus x, which gives the Taylor series here. Now, when you have a series, whether it's a power series, that is, it has a variable x of increasing power, or x minus 2 of increasing power, or some other series, what you would like to know is, where does that series converge? For some values it may converge, and some values it may diverge, and you'd like to know what is the set of values where it converges. Common way to talk about that is through the radius of convergence. Let's say we have the power series here, which looks like the Taylor series expansion about 0 for the function 1 over 1 minus x. For some x values, this may converge and some may diverge. Let's consider various points x that are real numbers and see what we get. If we let x be equal to 1, we substitute that in and we just get an infinite sum of 1s. And of course that will diverge to infinity. Remember that divergence doesn't always mean it adds up to positive or negative infinity. It just means that it does not converge to a particular finite number. When we plugged in x is equal to 1, we saw that the series diverges to infinity. Let's try another value for x. Let's try x is equal to 1/2. If we substitute that in, then what we find is that sum is equal to 2. And of course that converges to 2. Therefore, for some values, we have a divergent series, and for some values, we have a convergent series. We would really like to know what are all the values where it converges and what are all the values where it diverges. As we said, for some values, the series converges, some it does not. Now, for any series, you'll find that the point you center around, you'll automatically have convergence. The reason being, taking your power series, let's say where the coefficients are c sub n, and then we have x minus a to the n. And notice this is just a power series in general. It's like a Taylor series, except for the fact that these constants can be of some other form besides the derivative divided by a factorial. This is a little bit more general than a Taylor series. A Taylor series is a power series, but a power series does not have to be a Taylor series. If we have this power series and we substitute in the value, let's say x is equal to a, well then, of course, what happens is you get a minus a everywhere, which is 0. And the only time you won't get 0 for the term is when we're taking n is equal to 0. So in that case, you just get Cn. But Cn is just a number. So the series converges to Cn. That's a finite number. And therefore, it's a convergent series. That'll always happen. It doesn't matter what the Cn's are. They'll just be some numbers, so we get convergence. The question is, how far away from the value a can we get while still being convergent? So the notion is you have an interval around a such that as long as you stay in that interval, your series will converge. And as soon as you pass beyond that interval, now your series will diverge. Where note, we could have the endpoints here between the convergence and divergence. That point in between, we could have convergence there or divergence. Same thing with the other point. We could have convergence there or divergence. They could be different. We could converge on the right endpoint. We could diverge on the left endpoint. We could diverge at both points. We could converge at both points, and so on. Now, this distance from A to the edge, where it goes from converging to diverging, that is what's called the radius of convergence. And it does end up being that it's symmetric. So we can go the same distance to the right, same distance to the left. Now the question is, how do you find the radius of convergence? The answer to this is using the ratio test, also something that you would have seen in calculus 2. The ratio test says that if you take this following limit, which is the ratio of what you're summing up, where the first one has n plus 1 and the second one has n, or we're taking the n plus 1 expression divided by the n expression. That, because of the way these cancel in magenta, and because x minus a has nothing to do with n, you're just left with this limit. And if you get that this is less than 1, then this thing converges. Alternatively, if it's greater than 1, then it diverges. And if it's equal to 1, you're not sure. This limit here will help us determine what the radius of convergence is. In particular, let's take just this expression and rewrite it. Say the limit of this ratio is a finite value. Since we're taking absolute value, it will be positive. And a slight rearrangement gives us that x minus a is less than 1 over L. This is our radius of convergence here. That is, we have a radius of 1 over L. Now let's compute the specific radius of convergence for a given series. Say we have the series x to the n, where we start at n is equal to 0. A computation of the limit we have just seen gives us that x should be less than 1. Now this is a series that is centered around 0, and we find that the distance from x to 0 should be less than 1. Therefore, if we graph this, what we have is anything between -1 and 1, strictly, is going to give a convergent series. Anything beyond distance 1 from 0 is going to give divergence. And now the only question is, what is happening at these two endpoints? Let's let x be equal to -1. Substituting that into the series, what we get is something like this. Now this is a divergent series because you can group the different elements, and what you get are different values depending on how you group them. So for instance, we can get a grouping like this, and that'll give us 1. Another grouping will give us 0. And since we don't get the same thing, we have a divergent series. Now the question is, what about x is equal to 1? In that case, we're just adding an infinite number of 1s, and we get that it diverges. Therefore, since there's divergence at both of the endpoints, we fill those in as yellow for a divergence. Now again, these could both be cyan endpoints. One could be yellow, one could be cyan. There are all the different possibilities. Now let's consider another series. If we look for the radius of convergence of this series, doing our computation, what we get after doing all the algebra and then taking the limit is we get infinity. The reason for that is this is degree 3 polynomial in n, and this is a degree 2. So the degree 3 will, of course, eventually outpace the degree 2. Now what this means is, even though we have convergence at 7, since this is a power series centered about 7, since the limit is going to be infinity, it will never be a finite number, and certainly never be less than 1, for any x value except for 7. Therefore, no matter what x is, if it's not 7, then you're going to get infinity, and infinity is certainly larger than 1. Therefore, it's divergent everywhere outside of just the point 7. And one way we say that in terms of radius of convergence is we say the radius of convergence is 0. There essentially is none. The point is as far as we can go. The point we look at the series around. Now, it's often useful to differentiate and anti-differentiate series. To do so, you would do this term by term. Supposing we had this series, just 1 plus x squared. If we were to differentiate the whole series, we do it term by term. First we get 0, then we get 1, then we get 2x, then we get 3x squared, and so on. And another thing we can do is, if we have a formula here, we can use that formula to take the derivative. So we just apply the power rule in each case. Now the power rule is not exactly what we're doing here, because we don't have x to the n for n something non-zero. But it does fit the form in this particular case because it would give us 0 times something here. But this is a little bit of an abusive notation in the case of n is equal to 0. But for the case of n is equal to 1 and beyond, this is certainly a perfectly fine formula to have. But that's it. Just differentiate term by term. Taking the antiderivative, same exact thing. Do it term by term. Another thing that's useful to do with series, especially when we look at series solutions to differential equations, is changing the index, or at least the starting value of the index in the series. Suppose we start with this series where we have an n is equal to 2 being our starting value, and the formula is a sub n x to the n plus 3. Now writing this out, we would get a sub 2 x to the 5th, because 2 starting n value is equal to 2 plus 3. And then we increase that to 3 and 6. We increase that 4 to 7. And that's because we index over n, and each time we increase n by 1. So we have n is equal to 2 here, n is equal to 3 here, n is equal to 4 here, and so on. Now we can write exactly the same series, but change the starting value of the index. Here, we write the series where instead of starting at n is equal to 2, we start at n is equal to 0. Now that means if we want these to be the same, which they are, in the sense that here's 2 and here's 0 plus 2, here's 5, here's 0 plus 5, we have to change the formula. In particular, when we start at n is equal to 2, we can have just n here, because that will give us a2. If we start at n is equal to 0, we can't just have an, because then we'd start at a0. What we want is to start at a2. So because we work with n is equal to 0 here, we add 2 to it. Notice we reduced from 2 to 0, and then we increase this n from n to n plus 2. Likewise, here we're starting at n is equal to 0, but we want to start at n is equal to 5, so we take n plus 5, and that will give us the 5 here. Where again, we went from 2 as a starting index down to 0, so we subtracted 2 there, and then we increased this value by 2. So we went from n plus 3 to n plus 5, we went from n to n plus 2. And that's it. I hope you found this video useful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.